Hello, my shimmering stars. Today I, Shaurya Grover, welcome you all to this amazing platform of PW English. Students, I welcome you all to your Nexus Batch, and today we are going to start with your chapter P block elements, and this is going to be lecture number 2. So I guess students, you have done the previous session and you were now able to understand about the P block elements, and we have categorized, as per the groups, group number 13, 14, 15, 16, 17 and 18. And I have already told you that group number 13 and 14 basically is going to come in class 11th, and 15 to 18 is going to come in class 12th. So I hope so you have done basically the general properties with regard to group number 13th, that is boron family. Now it's turn to move further into boron family, and let's understand a wonderful concepts over here. Yes, everyone. So now in this particular session, what are we going to do? How are we going to proceed further? Let's talk about it. So students, as I've already told you, this is your lecture number 2. Let's correct it over here. It's lecture number 2 though of the P block elements chapter, and over here, students, we are going to study about boron now in detail, the compounds related to boron. Let me tell you, it's very basic things about boron, and the boron family that we should know, So we are going to understand them one by one. So before starting on to the compounds, I'll be talking with you about the oxides and the hydroxides of the boron family that was still left over. So let's start with that portion, students. So this is going to be the, sequence of how we are going to cover today's session. So now students, starting with my very first initial part, let me tell you that I am talking over here about your, the oxides and hydroxides of the boron family with regard to the boron family. Yes, everyone? Okay. Now discussing about the oxides and the hydroxides part, we very well know what are the members of boron family. Boron, aluminium, gallium, indium, and then comes the thallium part, right everyone? So these are the members of boron family. Now talking about what are basically the oxides form over here. So students, we very well know that they generally, have +3 oxidation state. They generally have +3 oxidation state, my dear students. And if I'll talk about the compounds that we can create. Now, what are oxides basically? When they're reacting with oxygen, it's but obvious, right? So when I'm saying that, let's say boron basically has +3 charge, and oxygen we know that it has -2 charge. So what is the compound that we are going to get over here? It's a very simple. Their charges will come, at the base. Now it is going to act as a scissor. How? Just see over here. The charge of oxygen will come at the base of boron, and the charge of boron will come at the base of oxygen. So it forms B2O3. That means in general, if I'm talking about the oxides that we can create for the boron family, what it will be, students? It is going to be E2O3. What it is going to be? It is going to be E2O3. Now let's come back to this point over here. Ma'am, what are the oxides you're going to create from these all? So it is going to be B2O3. Then it is basically Al2O3. Then it is basically Ga2O3. Then it is basically In2O3. Then it is basically Tl2O3. Now many of you will say that, ma'am, how can this exist? Let me tell you, it is very, very unstable. It is basically unstable. It is basically unstable, students. Do remember this part. Now coming back over here, students. Now let's talk about this all over here again. Let me tell you, B2O3 is acidic in nature. It is acidic. Al2O3, and if I'm talking about Ga2O3, they both are amphoteric in nature. What are these? Amphoteric in nature. Amphoteric in nature. Now, what do you refer to as amphoteric? The one that, has a characteristic of both acid as well as the base. So, basically, this is amphoteric in nature. And if I'll talk about the last one now, but obvious that if it is acidic, if it is amphoteric, the other ones are going to be, ma'am, basic in nature. Other ones are going to be, ma'am, basic in nature. Let me tell you, students, about B2O3. B2O3 is highly acidic, or I would say it is more acidic. I would say it is more acidic and less basic. This I am only talking about right now about the oxides, students. Only about the oxides over here. Right, everyone? And Tl2O3 basically is unstable. You very well know the reason why. Because over here, the thallium over here in this particular, compound, thallium is present in plus 3 oxidation state, which is unstable, my dear students. Which is what, ma'am? Which is unstable. Okay, we very well know why it is unstable. Due to inert pair effect, plus 1 oxidation state is basically your stable oxidation state. Now, what is inert pair effect? I have already explained in the previous class. That is basically, the shielding process. Okay, that means the inner electrons basically won't let, the electrons to participate. S electrons won't participate in bonding. Okay, now this is what is inert pair effect, that only the outer ones are going to participate, because as you come down the group, you basically observe that it is no more the same state. If you have NH2 NP1 state over here, the general electronic configuration, and as you come to the last, element over there, other groups also come in between, due to which what happens basically, for example, if I'll talk about that part, the NH2 electrons is so close to nucleus that nucleus does not let them to participate in bonding. Hence only NP1 electron is going to participate and is going to show only plus 1 oxidation state, right? Because only 1 electron is participating. That's why due to inert pair effect, we can say the reluctance, okay, of the S electron to participate in bonding is basically the inert pair effect that is occurring over here, right? So this is all about, students, oxide. Everyone just write down. Now the question that they're going to ask you, they're going to ask, which of the following is amphoteric, which of the following is basic, which of the following is acidic. So I've already told you this part over here. Everyone just write it down, so that now I can start with the hydroxides part. Everyone just take a minute and write that down. Just take a minute and write that down. Let me write hydroxides over here only. That will be much better. See, now when I'm forming hydroxides, we very well know in hydroxides we have OH negative, right? And they basically have general plus 3 oxidation state. So what are they going to form? They're going to form BOH thrice. Then the next one is going to be what? AlOH thrice. The next one is going to be what? GaOH thrice. The next one is going to be what? INOH thrice. And the last one is TLOH thrice. Right, everyone? Now, it is almost the same thing. It is also acidic, but it is weakly acidic. Okay. Then the next two that I am talking over here, they are amphoteric, and the last two basically are your basic. Okay. So, this is about hydroxide, students. So, BOH thrice basically is weakly acidic. Then we have two amphoteric ones. The aluminium one, that is aluminium when it forms hydroxide, is amphoteric, even gallium. And indium and thallium, basically they are basic. Clear, everyone? So, just take a minute and write both the types about oxides and the hydroxides with regard to the boron family. I guess this is clear to each and every one of you. Now I'm going to start with the compounds part of this. Now we shall be proceeding with the compounds part. But before that, there are some important trends, okay, and some anomalous behavior properties of boron. See now, let me tell you, if I'm talking about the anomalous properties of boron, we basically know that boron has small size. Okay, and there are such, more characteristics, more properties due to which it has some different behavior in comparison to the others. What's that, ma'am? See, the trichlorides, bromides and the iodides of all these elements being covalent in nature are hydrolyzed in water. Okay. Next part, species like tetrahedral and octahedral, except in boron, exist in aqueous medium. Just leave the boron, rest basically exist in aqueous medium. It is due to the absence of d orbitals that the maximum covalency of boron is what? 4. Why? Because there is no d orbitals that is present over here. No d orbitals. It has small size absence of d orbital. That's why it has a anomalous property. Next part. Since the d orbitals are available with aluminium and other elements, the maximum covalency can be expected beyond 4 in that cases. Because in that cases what happened, they are going to provide the d orbital, the empty d orbital, and that can participate in bonding process also, because d orbital is available over there, right everyone? So basically in the case of except boron, the other elements can have more than 4 as a covalency. That means it can create more than 4 bonds, right? Now see, boron trifluoride easily reacts with Lewis bases such as NH3 to complete the octet around the boron. So basically they are creating a coordinate bond over here. As you can clearly observe that nitrogen is sharing its lone pair of electrons with BF3. Clear everyone? So now the next part, the next properties with regard to boron. All boron trichlorides except BF3 are hydrolyzed to boric acid. That means they can be converted to boric acid H3BO3, but BF3 cannot be. BF3 cannot be. Remember that. Next, the increasing order of Lewis acid character is already given to you over here. This is the increasing order, and let me tell you, this is quite important. From this basically they are going to ask sometimes questions in the competitive part as well. Now the next part, BF3 is expected to behave as a stronger Lewis acid than BCl3 because of more electronegativity of fluorine, but practically it is less acidic in nature. Next, BF3 has delocalized dative pi bonds from fluorine to boron, which is called back bonding. Back bonding ability to more with fluorine atoms, as BF bond involves overlap of almost equal orbitals, that is 2p overlapping takes place. Okay, now I'll explain you something, about banana bond and all of that part. Okay, so now students, first of all, I'm going to start, first of all, I'm going to start with diborane. I'm going to start with the very first compound, that is diborane, and then I will be doing borax. Okay, so basically this is how I'm going to proceed over here. Now see students, when I'm talking about diborane, that is B2H6. First of all, let me tell you, I will talk about BH3. See, basically students, BH3, if I'm talking about, it does not exist. BH3 does not exist. BH3 can exist in the form of dimer. In the form of dimer. What is that exactly? That is your basically diborane. That means BH3 exists in the form of B2H6. It exists in the form of B2H6. Why is it so? Ma'am, why BH3 does not exist? What is the reason behind it? Let's explain that. See, it basically does not exist. Why? Because see, if you are creating a bond, with boron, see how many electrons are there. Now, it is basically getting attached with hydrogen, Count the number of electrons over here. Now see, it's 1, 2, 3, 4 and 5, 6. Basically here we have 6 electrons in the case of BH3. In case of BH3, when we have 6 electron students, it is basically your electron deficient species. It is basically your electron deficient species. And in order to make it stable, what it does? It reacts with itself. What it does? It reacts with itself. BH3 plus BH3. It will form what? It will form B2H6, diborane. Now, how is the structure of diborane? Now, after diborane is formed, is it electron now? Here electron, if it is not electron deficient. It is also electron deficient, but it is more stable, than BH3. So let's explain about it. Let's discuss about it now. What is the structure of B2H6 and how I can say that? And let me tell you students, in B2H6, we are going to study a different type of bond, that is the banana bond. Let's understand about that as well. So after that, I'm going to read all the properties over here. Okay. So now I'm talking about B2H6. Okay. Now students, first of all, let's discuss about boron. We know that boron has an atomic number 5. So it is going to be 1s2, 2s2, 2p1. This is the electronic configuration of boron. And if I'll talk about in the s orbital, we have 2 electrons. In the p orbital, students, we only have 1 electron. In order to participate in bonding, what it is going to do? This basically 1 electron will transfer over here. What you are going to get? 1 electron in the s and 2 electrons in the p respectively. like this over here. Now students, how many hydrogen are going to make a bond over here? Ma'am, 3 hydrogen, and it also has 3 electrons over here. 3 hydrogens are going to come and create a bond with that part, right? But now let me tell you, when BH3 was present, when BH3 was created, it was created in the same way. But now two BH3 are going to combine together and going to create B2H6. How it is going to be formed? See, let me tell you, boron basically will push itself to sp3 hybridized configuration. And when it is going to push itself into sp3 hybridized configuration, how it is going to show itself? So basically, this is going to be somewhat structure for B2H6. Yeah. This is going to be the structure for B2H6. Now, let me explain you how. See, in one boron, we basically have 3 electrons. Now, when I'm saying that it is going to push itself into sp3 hybridized configuration, then that means all of these orbitals are going to combine with each other, right? Then only sp3 hybridized configuration will be created. Now, see students, if you remember, we did, the hybridization concept in the chapter 4th of chemical bonding. And I told you over there, whensoever hybridization is going to take place, it is not going to take place between atomic orbitals. It is going to take place between hybrid orbitals, right? And hybrid orbitals basically have same energy, but atomic orbitals does not have that. Now, if I say that in general, 1s and 3p, are going to combine with each other, they are going to create sp3 hybridized state, right? And all of the 4 basically will have equal energies over there. Very simple part. So now when I'm coming to this part, let's see that boron basically, if it is pushing itself to sp3 hybridized state, then we can see that it contains 3 electrons in this. It contains only 1, 2 and 3 electrons over here. No. 1, 2 and 3. So let's say 1 electron over here, 1 electron over here and 1 electron over here of this boron I'm talking about. Now let's say about this boron. Now what is the state about this boron? If I'll talk about this boron, let's say 1 electron over here, 1 electron over here, 1 electron over here and let's say 1 electron over here. Now students, we very well know that this is boron which we have represented, and if I am talking about that how many hydrogens are there in this particular structure, so it is basically 6 hydrogen atoms that are attached to this particular structure. And hydrogen atom, students, is basically spherical in structure. When it is spherical, we can say that one hydrogen will be over here, another hydrogen will be over here, another hydrogen will be over here, another will be over here. We know that the electronic configuration of hydrogen is what? It is 1s1 with atomic number 1. So it is s orbital, so it is spherical in shape. Now, 1 electron will be of hydrogen, 1 electron will be of hydrogen, 1 electron will be of hydrogen, 1 electron will be of hydrogen. How many hydrogen atoms are connected now? Ma'am, 1 hydrogen, 2 hydrogen, 3 hydrogen and 4 hydrogen. Okay, that means still 2 hydrogens are left. Now, where will be the 2 hydrogen are going to combine? So, one of the hydrogen is going to come over here, another hydrogen is going to come over here, and this is electron of hydrogen, this is another electron of hydrogen. Now, this bond we can clearly see this is basically the sharing of electrons, the covalent bond that is created out. But what about this bond? Let's understand the students. Over here we can clearly see that S and P are basically combining with each other. Let me take another color. Yeah. We can see that 2 orbitals. Here 2 orbitals are overlapping. Here 2 orbitals are overlapping. But here how many orbitals are overlapping? Here 2 orbitals are overlapping and there is 2 electrons, right? In all of the 4 situations. But over here 3 orbitals are overlapping. 3 orbitals are overlapping with how many electrons? With only 2 electrons. With only 2 electrons. 3 orbital overlapping with only 2 electrons. So this is a different kind of bond that will be created, which will be referred to as banana bond that is created. Now let me explain you about it in detail. But first of all, I want you people to at least write down, draw the structure. I'm going to draw the structure now in detail, how banana bond is being formed and what is basically the characteristics of that as well. Everyone just take a minute, draw these structures so that I can move on to the next part. Yes. Yes, shall we? Now one more thing, students. It is also electron deficient. Here also electron deficiency is seen, as we can see one of the orbital is empty, so it is also electron deficient, but it is quite stable in comparison to BH3. Now see, if I have to represent it like this is boron. Okay, now I have to show the bonds with hydrogen. So basically this is the structure of B2H6, right? In which if I have to represent electrons, there is one electron over here, another over here, one over here, one over here. Now see, one over here, one over here, one over here, one over here. And here if I have to represent, in general, so one electron, now see, this complete basically bond contains only two electrons. This complete bond over here contains only two electrons. Though there are three orbitals, it is going to be like this, yeah. Though there are three orbitals over here, but you can clearly observe that the three orbitals overlapping contains only two electrons in between. Remember students, this type of bond is basically banana bond, which is also electron deficient. This is also electron deficient. Now let me draw in 3D. Let's discuss about the 3D structure of it. So in 3D, students, in 3D it is going to look like this. Students, basically see what is happening over here. If I'll talk over here, 1, 2, 3, 4, 5, 6. 6 basically, atoms are in same plane. That means the boron hydrogen bond, total how many bonds? Total 4 bonds in same plane. Now this is the one plane, where one boron and they are attached to two hydrogen. Now let's talk about this. These hydrogens are referred to as the bridging hydrogens. These hydrogens are referred to as the bridging hydrogens or the bridged hydrogen. This is basically, these hydrogen is bridged hydrogen or the bridging hydrogen. Now when I'm talking about this plane, let's talk about this plane. So this hydrogen, two bridged hydrogen and two boron are in same plane. When I'm talking about this plane, see, when I'm talking about this plane, it is going to cut these two hydrogen and these two boron. But when I'm talking about this plane, it is cutting one top hydrogen, one bottom hydrogen, which are bridged one, and two of the boron atoms, right? So when I'm talking about this plane, the other plane, this plane, basically in this plane, two bridged hydrogen are there and two boron atoms are being cut. Right, everyone? Just write down, students, and you can also write over here. This I am talking about is the terminal hydrogen. The terminal ones. These are the terminal ones. And the top and the bottom one is the bridged hydrogen. Everyone. Just write it down. Everyone. Just take a minute, students. Write down the structures. 6 atoms I have written. If you want to write, you can clearly write 4 terminal hydrogen and 2 boron atom. And over here, it's 2 bridged hydrogen and 2 boron atom. 2 bridged hydrogen and 2 boron atom. Yes? Clear, everyone? Is it clear to each and everyone? Just write down, students. Done with this part. Now see, this is also referred to as this banana bond. If I'll talk about the banana bond, if I'll talk about, this is basically, here we can see 3 orbitals with 2 electrons. So we can even write it like this. 3 central metal, with 2 electrons, having 2 electrons. Now students, let me tell you more about B2H6. It is colorless and it acts as a fuel. More things students about the angle that they are going to ask you such questions on angle. Let's talk about that as well. I'm going to draw it over here again on the next slide. Let's see. Say if this is like this. Let's say that students, this bond length is A and this bond length is B. Okay, let's say that this is alpha angle and this is beta angle. So I'm going to write things over here. What is A? A is bond length of terminal hydrogen and boron atom. Okay, alpha is the angle between HBH. Now here these are terminal hydrogen, the central boron, and then again the terminal hydrogen. Okay, so this is the bond angle between that. Now what is B over here? B is bond length of bridged hydrogen and boron, and beta is the angle between bridged hydrogen, boron and the bridged hydrogen. This one. Here hydrogen is bridged one, which is creating a bridge like structure. Clear everyone? First of all, write this down. Now I'm going to tell you one order over here. From which questions are generally asked. See, alpha will always be more than beta and basically A will be less than B. So this is the order that you have to remember with regard to B2H6. With regard to B2X's, that alpha is more than beta and A basically is, less than the B. A basically is less than the B. Clear everyone? Just take a minute students, write each and everything out over here so that now I can move on to the next part. Clear everyone? Done. Now let me tell you why BH3 basically is possible, not BCl3. Why? Because here chlorine basically has a larger size. That's why this is not possible, and it is also possible because it has a smaller size. It has a small size. And hence it cannot exist because it is an electron deficient species, so it can exist in the form of dimer, that is B2H6. Clear everyone? Now let's talk about it in detail students, the other characteristics. See, binary compounds of boron and hydrogen are called boron hydrides. Okay, when hydrogen combines with boron, it creates boron hydrides. Now these compounds form following two types of series. The very first is BNHN plus 4 series, and the second one is BNHN plus 6 series. Okay, so you have to put the value of N, you will get the number. For example, if I put value of N as 2, it is B2H6. If I'll put it as 5, it is B5H9, like this. Okay, and if I'll put it value as 4 over here, it is B4H10, B5H11 in such a way. So it creates two kinds of series, and they basically are referred to as the hydrides of boron. Right everyone? The next part, how are you going to prepare it? What is the preparation method in order to create diboron? Now see students, first method is when you are going to react it with lithium aluminium hydride, LiAlH4. What it is exactly, ma'am? It is lithium aluminium hydride. It is lithium aluminium hydride. So basically when you're going to react it with BF3 students in the presence of ether, you are going to get your diborane, that is B2H6. This is one of the methods of preparation. Now comes the laboratory method, that in lab how you're going to prepare it. See, it involves the oxidation of sodium borohydride. Now what is sodium borohydride? NaBH4. And you're going to do its oxidation reaction in the presence of what? In the presence of iodine, again with ether. So you're going to get B2H6 and NaI and H2 basically. Sodium iodide and H2 basically is the byproduct obtained over here. Clear everyone? Now this was about structure. I guess you all have written this. You have drawn this part as well. Yes. Now let's talk about the properties. I have already told you that this is a colorless gas and it also basically it is used as a fuel. Okay. Next part. It is highly toxic and highly reactive with with a boiling point of 183 Kelvin. No need to learn the boiling point, just the properties you should know about it. Next part, it catches fire spontaneously in air. So when you're going to react it in the presence of air, it is going to catch fire and explodes with O2. Reaction with oxygen is extremely exothermic reaction. Yeah. Reaction with water is instantaneous and you are going to obtain the the hydroxide of boron, that is BOH thrice, which I have already told you how it is going to exist. Boron has a +3 oxidation state, OH has -1 oxidation state. So you create BOH thrice. Simple part, easy. Yes, everyone? Now, if I am talking about the chemical properties with regard to this, so diborane reacts with ammonia, but the product depends upon the condition. Now, what are the conditions? Let's see that. If we are reacting it with ammonia with a lower temperature and you take a ratio 1:2, okay, so you will be obtaining B2H6.2NH3. It can be written in such a way also, okay, which on further heating will give you inorganic benzene. Now many a times question is asked, what is an inorganic benzene? Okay, so many of the students just they correlate it with organic chemistry, but let me tell you, it is very different stuff. Here you have nitrogen over here, and how it is created when you react it with ammonia, diborane. For example, if you react diborane with ammonia at higher temperature, students, directly inorganic benzene is obtained, that is basically borazine, and the formula is B3N3H6. Now I am repeating, this is very important. That is inorganic benzene, it is B3N3H6. B3N3H6, everyone, just write it down. This is about the chemical properties with regard to that. Right, everyone? Now the structure part, which I've already explained, but yes, you can create your notes over here. You can write the most important points from here. So what are that? In diborane, after diborane, the 4 terminal hydrogen atom and the 2 boron atom lie in the same plane, and the 2 bridging hydrogen atom lie above and below this plane. Yeah. The 4 boron hydrogen bonds are regular 2 center 2 electron bonds. I told you that if I'll talk about this one. See, this is 3 center 2 electron bonds, and this is basically 2 center 2 electron bonds. This is basically 3 center 2 electron bonds. Clear? Simple? Easy? Yes, ma'am. Now, the 4 boron hydrogen bonds are regular 2 center 2 electron bonds, whereas 2 bridging boron hydrogen bonds are 3 center 2 electron bonds, which are called as banana bond. Now, question is generally asked from banana bond. It is 3 center 2 electron bonds, everyone. Is it clear to each and every one of you? Yes, ma'am. Okay. Now, students, this is the structure which I have already explained you. This is the structure which I have already explained you over here. Yes, done. See, A basically bond length is less than the B, no? And alpha basically angle is more than the beta angle, right? So these are the values, and in general, if you want to draw the structure, it is going to look like this. It is going to look like this. Clear, everyone? You can draw these structures, students, now, so that I can start with the next part. Just take a minute, draw the structures so that I can now start with the next part. Done? Okay, that's great. Now, students, I am coming to the next compound of yours. That is basically about Borox. Okay, now see, what is the formula? Na2B4O7.10H2O. Now this is another compound of borax, that is Na2B4O7.10H2O. Now how it is going to exist? Let me tell you first of all the structure. Create 4 borons like this. Then create oxygen-oxygen linkage in such a way. Then link any of the 2 boron with oxygen, any. For example, if I am linking these 2 borons with oxygen, it is going to be like this. Now, let me tell you, in the borax structure, students, in the borax structure, here it contains all kinds of bonds. Ionic bond, covalent bond, coordinate bond, all kinds of bond exist over in the borax structure. All kind of bonds basically exist over here. Now see students, after this if you have done, basically you can see that this is, the covalent bond that is created. Now see, here it is 2 OH attached properly, and now comes the coordinate bond. This is basically going to be the coordinate bond like this with OH. Now in order to represent coordinate bond, what we can do is, we can erase this bond and put a negative charge on the boron. So this is basically the coordinate bond that is created. And now if one Na positive comes close to this, this creates an ionic bond. Clear everyone? So basically this is the exact structure, and then you have 8 H2O molecules surrounding it. So basically when I'll keep this 2 Na positive outside, this is what I've written over here close to it. This is your ionic bond, these are your covalent bonds, and this is your coordinate bond that is created. Clear? This is the borax structure everyone, just write it down. This is the borax structure. Okay, it is basically white crystalline powder. It is basically white crystalline powder and has a cyclic structure. Everyone. Just write it down, student, about borax. Yes. Clear? You need to learn the formula also of borax. Moving on to the next one now, the preparation. How can you prepare it? What is the preparation method? See, it is found in nature but can also be prepared by following method. What are it? Borax is obtained by the action of Na2CO3 and orthoboric acid. So when you're going to react it with orthoboric acid, you're going to get what? Na2B4O7, CO2 is released. Na2B4O7. Now see students, what are the properties? I have already told you it is white crystalline powder, right? It is less soluble in cold water. Now this is important, highlight everyone. Just mark it as important. It is less soluble in cold water but more soluble in hot water everyone. Next part. In aqueous solution, it is alkaline because of its hydrolysis to weak acid, that is H3BO3, and strong alkali NaOH. Okay. You can learn this reaction, students, as a chemical property over here. Now let's talk about, the action of heat, and let's talk about the borax bead. Okay. See, when borax powder, that means Na2B4O7.10H2O, it is heated, it first swells due to the loss of water in the form of steam. But at 740 degrees Celsius, if I am talking about at 740 degrees Celsius, see what happens. Basically, all the water molecule goes out and you're going to get the simple form, that is Na2B4O7. Now, this Na2B4O7 on reacting at 740 degrees Celsius, you are going to get what? A colorless, transparent borax bead you are going to obtain over here. A colorless, transparent borax bead is going to obtain over here. This is very, very, very important part. Very important part. Clear everyone? I hope so you all have written the reactions. Shall I move on to the next now? Can I? Okay. Now see students, let's talk about the borax bead test. Let's talk about it. Let's discuss about it. Now see, borax react with certain metal salts like Ni plus 2, CO plus 2, Cr plus 3, Cu plus 2, all of that to form colored metal metaborates. Okay. Now the color of the metaborate can be used to identify the metallic ions, okay, the cations in the salts. Okay. So for example, if I have this form and I'm going to heat it, first of all, I will be obtaining Na2B4O7, which I have done in the previous part only, and then I'm going to react it with 740 degrees Celsius. At 740 degrees Celsius, I will be obtaining borax bead, right? So this is a glassy mass, that is NaBO2 plus B2O3 is obtained. Now you are going to react this B2O3 with CuO. Let's talk with CuO. So what you are going to get? It will be containing which type of an ion over here? It will be containing Cu plus 2 ion, cation, no? It will be containing this cation, so it basically gets blue bead over here, right? So the color of the metaborates can be used to identify the metallic ions in it. For example, if you can see CuO plus B2O3 gives you blue bead over here, which I have already told you, which indicates that it contains Cu plus 2 ion in it, which shows that the salt contains Cu plus 2 ion in it. Yes, everyone. Now, what are the uses? It is used in the Borox bead test, in purifying the gold, students, as flux during the welding of metals, and in the production of glass as well. Yes, everyone. Simple, easy. Okay. Now, Diborane we have covered, Borox we have covered. Now, this is general thing about, let me tell you general thing about boron. General thing. Okay. 2 we have already covered. We have already covered the Borox. We have already covered the, we have done the Borox part. And we have covered the diborane part, right? So basically boron occurs in nature in the following minerals form. So this is the following minerals form in which it can exist as. Okay, that is borax first of all, then boric acid, then carnite, and then colomanite. Now you have studied this in metallurgy chapter also. If not in class 12, this is in your syllabus. Coming to, the extraction of boron. Now the extraction process basically is very, very simple. You can extract basically, the boron how? Let's see. By the reduction of B2O3, when you go into the reduction with either magnesium, sodium, potassium, this will occur in the absence of air, remember that. That means no O2 is involved. So you have Na2B2O7 and you are going to react it with HCl and H2O. You are going to get H3BO3. This H3BO3 on further heating will give you B2O3. And this B2O3, as I have told you, will react with magnesium, sodium or potassium in the absence of air. So when you are going to react it at high temperature, you will be obtaining your boron and their oxide will be liberated out, MgO, Na2O. Okay. Now it can also be prepared by 1-acryl method. Here you have taken Bi3 and you have done this basically in the presence of red hot tungsten. You got the boron over here and I2 is basically released out. Right. So basically these are the properties. It can exist in 5 forms, 4 of which are crystalline and 1 is amorphous form. Now all the crystalline forms are black in appearance and chemically inert. That means non-reactive. Okay. However, it is attacked at high temperature by only strong oxidizing agents. Students, remember that. Okay, such as a mixture of hot concentrated H2SO4 and HNO3 or Na2O2, that is sodium, okay, oxide we have seen. Now, but amorphous form is brown and chemically active. So, this is the difference between the crystalline and the amorphous form of boron. Now it's a reaction with air, students. This we have already done in the previous class, if you remember. I told you that impure boron can only form its oxide, but the pure one will not form. So it is less reactive, right? So it can form B2O3, only impure can form its oxide, the pure one cannot do that. Boron is used in the construction of high impact resistance steel, and since it absorbs neutrons in the reactant rods, okay, and boron carbide is used in abrasive, right? Now students, coming to the next part is uses of boron and aluminium and their compounds. What are their uses in general? So boron fibers are used in making bullet-proof vest and light, okay, composite material for aircraft industry. Next, the borax and the boric acid is used in the manufacture of heat-resistant glasses. Glass, wool and fiberglass. Borox is used as a flux, okay, basically, and it acts as a flux. So this is one of the, uses that you can study of them. Now students, the aluminium part that we are going to do, we'll be understanding the aluminium compound in the next lecture. Today's session was about the only compounds related to boron. So I'm just going to cut it over here because about aluminium we'll be doing in the next part. We'll be understanding about Al2O3 in detail. Right. So this session was all about the compounds related to boron and I guess you all are able to understand that very well. Let me tell you, I have done this complete session in detail about diborane and borax. So students, these two compounds you have to do in detail so that in next class, when I will be proceeding with the next topic, I want you people to answer me all the questions with regard to both of them. Right. Now students, I will be meeting in the next class. Till then, keep smiling, keep learning. Thank you so much and take care of yourself, students. Thank you so much. Have a good day.